Hey, what's up, guys? This is Chen here. So today, let's take a look at today's daily challenge. Problem number 542, 01 matrix. Okay, pretty straightforward, right? So we're given like a n by n binary matrix, and we need to return the distance of the nearest zero for each cell. Okay, and the distance between two adjacent cells is 1, right? So obviously, if the cell itself is 0, then the distance for the cell to the nearest 0 is obviously 0, right? So which means we only need to consider the 1 scenario. So this is the first one, right? All the other are 0, and for 1, obviously this is 1. Because from here, in any directions, we can have like 0, right? That's why the answer is 1, right? Pretty straightforward. And for this one, for example 2 here, right? So the 0 for this one is 1. For this one is also 1, right? Because we have 0 here. For this one is 2, okay? Because the nearest 0 for this one is either this one or this one, and the distance is 2, right? And for this one is 1, right? So that's it. And the constraints like 10 to the power of 4, and there is at least 1 0 in the matrix, right? So for this kind of problem, every time when you see the distance of the nearest 0, right, or the smallest distance, first thing should always be what? The BFS search, right? But to do the BFS search, if we do a brute force BFS search, basically, like I said, we only need to consider 1, right? So let's say for each one, if we do a BFS search for each one, then the BFS search itself will take m times n, right? Time complexity. And the worst case scenario for each of the one here, for each one we're gonna have like this time complexity. That's why it's gonna be a n square. Let's say n big N, right? N squared time complexity. N is equal to the m times n, right? And this will TLE. So that's why we cannot brute force do the BFS for each one, right? So and then how can we improve that? There is always like I think it's a common trick in this BFS search. Instead of search from the source to the target, we can also search from the target to the source, which means that instead of searching 1 to 0, we can search 0 to 1, right? So the benefit of searching 0 to 1 is that we can add all the zeros into a queue, right? All the coordinates of 0 into the queue, and if we do a BFS search here, we will every time when we reach a 1, then we can simply we're sure that that the current distance will be the smallest distance for this current one. The reason being is that since we add all the zeros into this queue, and we do a BFS search on all of zeros, right? So which means that we have considered all the possible 0 scenario, and we simply just need to do the BFS search once. And every time we reach 1 here, we simply mark the distance for that 1, right? And in that case, all we need to do is we just need to do a 1 BFS search. Yeah, I think that's it, right? Pretty straightforward. And for that, let's try to encode that thing. So we have n is going to be the mat 0, okay? And then we have a q, right? dq. So we have directions, right? We always need to define the directions here, 1, 0. Actually, after this BFS approach, there's another like DP approach that we'll be talking about later. So at the beginning, everything is 0, right? Excuse me. In range M, we initialize everything to 0, right? So that we don't have to worry about all the zeros. All we need to consider is the one case, right? For the 0 ones, the answer will be 0. And then we also need a visited, right, for the BFS template. So let's populate the queue then, right? For I in range of m, for j in range of n, right? Basically, if the mat I j is equal to 0, right, we add this 0 into the queue. Basically the coordinates, right? And then we're also gonna insert into the set. Okay. And then we have a distance, right, for the to maintain the current BFS. And then just a BFS template here. Wow, this one is not that not empty. We do this one length of the queue, right? And we do something later on. We do a distance +1. Actually, it's always a good habit, to finish the template first, and then you fill in the remainings. Because if this part is coming along, you may have forgot this part, right? So basically, just try to implement the entire template while it's still fresh, right? Your memory. Okay. So now for the BFS, right? So now we have ij is going to be the q dot pop left, right? And then we check basically if the I and j is 1, right? If this thing is 1, then we know, okay, we can update the answer of the current one with the current distance, which is this, right? Distant. And then the remaining is just like the BFS. Okay. So this we have seen this many times. So I'll just quickly code this thing here. Right. So for 0, new I m, and 0 between the 0 and n, right? For the new j, and the new I and new j are not visited, right? And the q dot append this new I, new j, this visited, right? Dot add this new I and new j. Okay, that's it, right? I think that's it. If I run this should just work. Okay, a few typos there, and submit. Cool, so it passed, right? So this one is pretty straightforward, right? The only difference is that, instead of do the BFS from the source from 1 to 0, right? We do it from 0 to 1. Okay. And that's that. Okay, so a second one is that, we can also use DP concept to solve this problem. So what does the DP concept mean? So for given given cell, right? If we know all the minimum, the the the, the nearest distance for all its neighbors, right? We have up, left, down, and right, right? So for a given cell, if we know all the minimum distance for all its neighbors, so what's the minimum distance for this one? Obviously, it's going to be the minimum of all its neighbors, right? The value. So that's basically the concept of DP here. And how can we know the neighbors, right? So for DP, right? So if we traverse this grid from top left corner to the bottom right corners, we can always, by the time we are at this I and j here, right? We know that the left one and the above one, right, can be we know that we can update the current one with the left one and the up one, because we know if we traverse from this direction, right, then we know the up one and the left one of the current one, it will be the smallest, right? Basically, we can use that to update this one. But if we traverse from in this direction, we don't know this part. We don't know the below one and the right one. So which means that with the first traverse, we can only do a partial calculation. Basically, we're only calculating the half of the neighbors, and in terms of the right one and the below one, right? What can we do? Easy, right? We simply reverse the traverse direction. We retraverse it from bottom right corner to the top left corner, right? So if we traverse in this way, now once we are at I and j here, we already have the values for the right neighbor and the below neighbor, right? So right, that's why we can simply just do this dp calculation twice. First time from first one is this direction, second one is this direction, and we update the same like cell twice, right? And we just get the minimum of above all those four among all those four like neighbors. And yeah, so that's the idea here. And okay, I think we can start coding here. So DP1 is also kind of straightforward. I guess we need this one for the DP. First one, the answer, right? So now the answer is going to be the system max size, because since we're calculating the minimum value, right? And we're gonna do this, initiate everything into the system max size. Okay. So the first loop is from the top left corner, right? In right? So first thing first is that if the mat I and j is equal to 0, right? We update the answer of I and j into 0. This is obvious, right? Else what? Else we check the left and up neighbor, right? But since here there could be no left or above neighbor, right? So we can do some little check here. Basically, the left is going to be the answer dot I j minus 1 if j is greater than 0, right? Else system max, right? So basically, if there's no left neighbor, I'll just set this one to be the system max. Similarly for the up one, right? Now this is going to be a I minus 1 and j, right? If this I is greater than 0. Okay. Now I can simply update the answer, which is I and j with two neighbors, right? Minimum of left and up, right? And then don't forget to do a plus 1, right? Because from the neighbor to the current one, the distance is 1, right? Okay, so that's that, right? And then the second time is that we simply need, since we only consider the left and up neighbor, we also need to calculate the rest two neighbors, right? So for this one, we reverse the order. Okay, minus 1, minus 1, minus 1. Okay, so here we have right and we have down, right? Up and down. Okay, so for this one, it's going to be a I j plus 1, but this one is going to be if the j is smaller than the n minus 1, right? So this one is like I plus 1 j if the I is smaller than the m minus 1. Okay, but here, so be careful, we cannot use this one here. Why is that? Because we also need to consider this the previously calculated aij answer here, right? Because this one we are not considering the left and up, we're only considering the right and down, right? So which means we have to do another minimum of the already calculated neighbor with the current one, right? Okay, and then return the answer in the end. Yep, so if I run the code, this should also work, right? Yeah, because this one, obviously the time complexity is also like two of big N, right? Because we have two for loop here. Yeah, I think that's it, right? I mean, it's pretty classic, either BFS or DP. I think BFS is kind of okay. I think it's kind of easy but for DP, I think one thing for DP is that we need to have this sense basically, uh, given like this 2D grid, right? If we traverse in this direction, you know, we can always consider the above and the left neighbor, right? Because we have similar like DP problems. Let's say we have different values here, 3, 2, 1. When we want to know like what is the basically the minimum value if we want to traverse from the left top left corner to the bottom right corner, right? Because we can always, I mean, in if the current person can only move either to the right or down below, right? That's why if we traverse this way, we can utilize the DP values of this up neighbor and the left neighbor, right? But in our case, for this one, actually, since we need to consider all four neighbors, right? We also need a way to calculate to find the right neighbor and the below down neighbor. That's why we need a second DP for loop in the reverse direction so that we can calculate the other two neighbors. Yep, I think that's it for this problem. And yeah, thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.